Hi, in this video, we want to take a look at ANOVA, but where we have more than two independent categorical variables. We're going to be talking about, that's right, factorial ANOVA. Okay, so our situation is I have three or more independent variables that are categorical, that is nominal or ordinal, and I have a response, a target variable that is numeric. And what we want to do, we want to see, are there differences in the population means defined by our independent categorical variables? All right, so previously we talked about one-way ANOVA, which is where we had one independent categorical variable. We talked about two-way ANOVA when we had two independent categorical variables. Now we want to generalize this to three or more. Now, factorial ANOVA actually covers one and two-way ANOVA, but usually when we say factorial, we're referring to three or more. The main effects interpretation will be the same. The interactions effects is going to be a little bit trickier than what we talked about previously in two-way ANOVA, because we'll have a much wider variety of interaction effects that we have to consider. All right, so let's dig in. Factorial ANOVA, or analysis of variance, is a statistical technique used to examine the effects of two or more independent variables on a single target variable. In contrast to one-way ANOVA, which analyzes only one independent variable, factorial ANOVA enables the exploration of possible interactions between different independent variables and how they jointly affect the dependent variable. All right, there are two primary outputs of a factorial ANOVA: the main effects and the interaction effects. For main effects, this refers to the effect each independent variable has on the dependent variable, ignoring the effects of all other independent variables. Now, the interaction effects, this refers to the combined effect of two or more independent variables on the dependent variable, which is above and beyond the main effects. In other words, the interaction effects check whether the effect of one independent variable changes based on the levels of other independent variables. All right, so in all ANOVAs, we're checking out main effects. And when we're talking about main effects, we're looking at just one independent variable at a time. Interaction effects, we're considering the combination of two or more independent variables. So when we're talking about three-way ANOVA, what we're going to end up happening is that for each of the three variables, I'm going to have a pair. I'm going to have a pair, and then I'm going to have a pair for interaction. That's three pairwise interactions. Also, I have a fourth of all three together. So in three-way ANOVA, I have four interactions that I'm going to be checking. In practical terms, factorial ANOVA can be used in various research fields to understand complex relationships. For example, in psychology, a researcher might use it to investigate how both age, independent variable one, education level, independent variable two, together influence income, which is my dependent variable, my response. However, it is important to know that factorial ANOVA, like any statistical method, has assumptions. The assumptions are normality, homogeneity of variance, and independence. And another one that we haven't talked about in the videos yet, I'll keep that a secret for a moment. And these assumptions need to be met for our conclusions to be valid. It also can become complex and challenging to interpret as the number of independent variables increases. All right, so now let's take it back for a moment and let's think about two-way ANOVA. So in the videos, I did one-way ANOVA, two-way ANOVA. Now I'm doing two or more independent variable ANOVA. I'm trying to walk it in. So let's back up and compare the two-way ANOVA just to make it a little bit easier for us to make sure we have our heads wrapped around this. Factorial ANOVA and two-way ANOVA are actually very similar to each other. Two-way ANOVA is a type of factorial ANOVA. It's factorial ANOVA, but only with two. The two terms are often used interchangeably, but they have a slight difference based on the number of independent variables involved. So factorial ANOVA, this is a broader term that refers to any ANOVA using two or more independent variables. Factorial ANOVA allows researchers to examine the main effects of multiple independent variables on that response variable, as well as the interaction effects between independent variables. Two-way ANOVA, this is a specific type of factorial ANOVA that only involves two independent variables. It allows for the investigation of the main effects of the two independent variables and the interactions between them. In other words, two-way ANOVA is a subset of factorial ANOVA, specifically when there are exactly two independent variables. If there are more than two independent variables, it's referred to as a three-way ANOVA, four-way ANOVA, and so on. But these are all just types of factorial ANOVA. I'm not going to go into three-way, four-way specifically. I'm just going to, at this point, I'm going to say factorial ANOVA, and that covers all the higher order ANOVAs. Okay, so now we have some assumptions about factorial ANOVA, and there's some new ones here. So the assumptions for factorial ANOVA are similar to the ones that we looked at for one-way and two-way ANOVA, but it gets more complicated because I got more independent variables. So my first assumption is that we have independence between observations. Each participant or observation should be independent from all others. This means that the measurement of any observation does not influence the measurements of other observations. Only this assumption, often this assumption is met by the design of the study. And so this is saying we're not in a situation where I have like time series that are autoregressive. Next assumption is normality. The distribution of the residuals, the difference between the observed and expected values, should be approximately normal for each combination of levels of the independent variables. This assumption can be checked by using plots, such as a QQ plot, histogram, or tests such as the Shapiro-Wilks. Next one is homogeneity of variance, the homoscedasticity. The variance of the data within groups defined by my combination of independent variables should be the same. This can be checked by using tests like Levene's test or Bartlett's test. When this assumption is violated, it may be necessary to use a more robust version of ANOVA, such as Kruskal-Wallis, or transform our data to get things the way that we want it to be. Next one is no multicollinearity. All right, so the idea here is that if, let's pretend for a moment, I have 10 independent variables. I got a whole bunch of them. And it's possible for me to take 5 of them, and when I have those 5, if I look at the dummy variable representation, if I can get the vectors of another's dummy variable representation using some linear algebra trick, if I can get the dummy variables of this one using combinations of these, then I have multicollinearity. That means I have redundancy in my independent variables. When I have redundancy in my independent variables, well, I need to get rid of something. All right, now, when this happens, this can be a very, very difficult situation to navigate in real life. But for us to have a valid test to run, we have to have no multicollinearity. So multicollinearity, for those who are not, who do not have a background in linear algebra, matrix algebra, just think of it as we don't have any redundancy in the informative value of our variables. This is more relevant typically in multiple regression than ANOVA, but it's still important. The independent variables should not be too highly correlated with each other, as this can cause problems in determining which variables are accounting for the variance in the dependent variable. Now, the next one is sphericity. This is an assumption that is needed when you have a repeated measures factor with more than 2 levels. The variances of the differences between all combinations of related groups are equal to each other. Violations of these assumptions may require the data to be transformed, or we use a different statistical test, like a non-parametric test. It's worth mentioning that ANOVA is considered quite robust to violations of the normality and homoscedasticity assumptions, particularly if we have a large sample size. If I have a huge sample size, it's probably not going to be much of an issue if I'm violating some of these assumptions. All right, so let's talk about the hypotheses that we're actually evaluating when we're doing our factorial ANOVA. So to break this down to be a little bit easier, I'm just going to look at three-way ANOVA, and hopefully that this gets the audience to understand this better. It gets more and more complicated. If I was to go four-way ANOVA, five-way ANOVA, and the list is just going to keep on growing of hypotheses. Here, we're going for understanding. We're in real life. The computer is going to do the work for us. And so we need to interpret and understand what's going on. The ability to generate the formulas and hypotheses is not as important. All right, so the more factors we have, the more main effects and interaction hypotheses that we have to work with, have to figure out, and the complexity of the hypotheses increases. In a three-way factorial ANOVA, we have three independent variables, and I'm just going to call them A, B, and C. And you're interested in the main effects of each variable, the interaction effects between each pair, and the three-way effects. All right, so I have three main effects that I'm interested in. I have three pairwise interaction effects. And then I have a singular three-way effects interaction I'm interested in. So I've got 7. All right, so the math here, number of variables I have, it's always going to be 2 to the power of the number of variables I have minus 1. All right, so we have 3 variables. It's 2 to the power of 3, 8 minus 1, 7. 7 for 3 main effects, 3 pairwise interactions, and 1 three-way interaction. So here are the main effects. And so here for variable A, we're checking to see if so in main effects, we only look at one variable at a time. We ignore all other variables. And I ask, does it look like each subgroup's average of the dependent variable is the same across all the subgroups? I want to check that. And I want to do that for each of these variables. Okay. And now I want to, and my alternative hypothesis is that at least one of these is different than another. Now, when we get to the interaction effects, so we're going to have pairwise interaction and three-way interaction. So the null hypothesis is that there is no interaction between the two variables. The alternative is that there is an interaction between the variables. And so we have that 3 times for three-way ANOVA. And then we have our three-way interaction. And our null hypothesis is that there is no interaction between the combination of all 3. The alternative is that there is an interaction between all 3. Now, something that we're going to do, most of the time, most cases, we start with the highest order interaction and we reach a conclusion regarding highest order interaction. If I conclude that the null is correct and there's no highest order interactions, then I will check the next ones like this. The idea here is that if I have a higher order interaction, all of like the simpler interactions that are contained within it. So if I have A, B, and C as a higher interaction, all 3 of them, then I have to have all 3 main effects and all pairwise interactions that I can get off of these. And so here, AB is, conceptually inside this pair is inside this interaction. So I have to have the AB interaction pair also most of the time, most conclusions. A and C is inside this higher order interaction. Therefore, the AC interaction probably should be in my model. And if here we have BC is in this interaction, therefore the BC pairwise interaction should be in there. Also, if I would also have all the main effects corresponding. And so if I have higher order going on, all of the lower order like within are included in there. So now I'm going to first do my higher order interaction conclusion. If I fail to reject the null hypothesis and I conclude that there's no three-way interaction, I'll start looking at the pairwise to see which of these will be reasonable to remove from the hypothesis test. All right, so now let's talk about the ANOVA table for factorial ANOVA. All right, so once again, I'm going to only look at three-way ANOVA just to make it a little bit easier for us to navigate and figure out. A three-way factorial ANOVA table is a summary of the statistical calculations performed during a three-way factorial ANOVA. It breaks down the variability in the dependent variable into components attributable to each independent variable, the main effects. Each pair of independent variables, two-way interaction effects, and all three independent variable combination, three-way interaction effect. It also includes a component for error or residual variance that isn't explained by the independent variables or the interactions. Here is what we will typically see in a three-way ANOVA table. We have our source of variation, our degrees of freedom, our sum of squares, mean squares, F statistic, p-value, and effect size. All right, so source of variation. This column lists the independent variables. Let's call them A, B, and C, and their interactions. So pairwise interactions and the highest order interaction, as well as the within or error and total variation. The degrees of freedom for each source of variation are calculated. For main effects is the number of levels of the factor -1. For interactions, it's the product of the degrees of freedom for each factor involved. So it's the number of levels -1, but then we do multiplication. The error degrees of freedom is the total number of observations minus the total degrees of freedom for the factors and interactions. For sum of squares, this is the variability accounted for by each source of variation. It is calculated directly for each row in the table. And the formulas are a little bit juicier for this column. Now, next to mean squares, this is the sum of squares divided by the respective degrees of freedom. So here in this column, we take sum of squares, divide by degrees of freedom. Boom, I get my mean squares. Next, we're going to get our F statistic. I'm moving pretty far to the right in the table at this point. This is the ratio of the mean squares for each effect and interaction to the mean square of the error. So this is the mean square of the main effects or their interaction, depending on which row I'm looking at, divided by the mean square of the error. This is used to test the hypotheses about whether the effects or interactions are statistically significant. Next, the p-value. The p-value is the probability of observing an F statistic as extreme or more extreme than the observed value, assuming the null hypothesis is correct. If the p-value is less than the significance level, usually 0.05, the null hypothesis is rejected in favor of the alternative. And so we're going to have a whole bunch of hypotheses. Now, the next one is effect size. The effect size is an optional but useful addition to the ANOVA table. R doesn't spit it out, by the way. It gives the proportion of total variance in the dependent variable that is accounted for by each effect and interaction. The key to interpreting the table is understanding that if the F statistic is significant, below 0.05, probably, it suggests that the variation attributed to the corresponding factor or interaction is statistically significant. It implies that there is a difference in the population means of the dependent variable across the levels of the factor or interaction. And we're going to look at a table. Note that the actual values in a real analysis would depend on the data used and the computation performed. All right, so I have main effect, main effect, main effect, interaction, 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 and then my highest order interaction. These three are the pairwise interactions. Then we have the error within, and we have the total. All right, so my degrees of freedom, number of levels -1. Here on the pairwise, it's the product of pairwise degrees of freedom. And here I have the product of all 3 degrees of freedom. And so then we'll have our sum of squares, which I'll talk about the formula in a moment. It's kind of juicy, so I just put it in a separate spot. But we have our sum of squares for A, sum of squares for B, sum of squares for C. Next, we have our sum of squares for our interaction. And then we have our overall interaction. We have our sum of squares error and our sum of squares total. Now, to get our mean squares value, I divide this value by that, boom. I divide this value by that, boom. Divide this value by that, boom. And I keep on doing this all the way down. So I get to here. All right, and again, here I've got my mean squared error. Now, to get my F statistic, remember that the F test is taking the ratio of variances and comparing it to 1 using the F distribution. All right, so I take the ratio of variances. So I take MSA divided by mean squared error. Boom, that's my first F statistic. I take my mean square B divided by mean squared error. Boom. Mean square C divided by mean squared error. Boom. Now, mean square pairwise interaction divided by mean square error. I get this. And I just keep on going through and doing this, and you see it happens a lot. So I get a stack of F statistics. Now, we take the numerator, degrees of freedom. We take the denominator, degrees of freedom. And we use the F statistic with those 2 degrees of freedom as parameters to figure out our p-values. All right. Now let's take a look at the formulas in Factorial ANOVA. Okay, so there's some stuff to look at here. There's quite a bit. In 3-way Factorial ANOVA, we will look at the main effects of 3 factors, the interaction effects between 3 pairs of factors, and the highest order 3-way interaction. Here's our formulas. So here I'm taking the average of my dependent variable for just one level of the first variable. So this is first level of A. Take the average of the dependent variable, subtract the overall mean. Take the second level of A, take the average of dependent variable, subtract the overall mean. Take the third level of A, take the average of the response variable, subtract the overall average. Keep on doing this over and over and over. Square those differences to make them all positive. Here I'm multiplying by the number of times I see a particular level of A's variable, and then I add it all up. And I repeat this for each of the 3 main effects. And so this gives me my formulas for each of these. What you want to do, you want to figure out this formula for one of them, and then understand that it basically just repeats for factor A, factor B. Now, for my pairwise interactions, so it gets a little bit more interesting. Here I take so I've got 2 variables going on. I've got, let's say, A and B. I'm going to take a level of A. I'm going to take a level of B. So every time I see that combination of A and B, I take the average of the target variable. Then I'm going to subtract the corresponding average for the A, corresponding average for the B, subtract them off, and then I add the overall average. Check that out. So now we're adding the overall average, while here we were subtracting off. I subtract the difference and do it, add and subtraction. I square the whole thing. I multiply by the number of times I see this combination for the A and B variables, and then I add them all up. And that gives me my interaction sum of squares. And I do that for all three. Now, it gets even juicier, it gets even more exciting for three-way interactions. So I consider three variables, they're my three independent variables. I look at the subpopulations defined by each three. So I take a level of A, a level of B, a level of C, and I look at when all the records that have this level of A, this level of B, this level of C, I take the average for the combination on all of them. Then I consider the average when it's that combination of A and B, not worrying about C, combination of when I have the A and C combination, average when it's B and C, and then I subtract all of these averages off. Next, I worry about just A. So I take the corresponding value of A here. I take the sample average for that level of A, and I add it on. I take this level of B, take the average of my response variable, add it on, and I take this level of C, take the average, add it on. Okay, and so then after that, I've got the global overall average, and I subtract it off. So you'll notice I take the average for the levels defined by all of the variables. I subtract off the pairwise levels of the variables. I add on the singular, and then I subtract off the overall means. Now here is the error or the residuals. So in this one, what I'm going to do is I take each individual observation, I subtract off the sample average for its level across all three variables, A, B, and C. So for A, B, and C, I look at so I take an observation, I look at its levels of A, B, and C. I take the average for all records for that particular combination of variables A, variable C, variable A, variable B, variable C, do subtraction, square it, and then I add all of them up. Then I do this for all of my possible combinations of A, B, and C, and that is my sum of squares error. And then my total sum of squares is observation minus overall average, square it, add them all up. Boom, we've got it. So now, we don't want to do this by hand. No, we don't want to do this by hand. No. We're not doing this with the calculator. We're going to have the computer do it. We're going to put it in R. We're going to put it in SAS. We're going to put it in the Python, jump, stata, whatever. Don't care. Just not doing it by hand. And so we really don't need to slug through this, but we need to have an idea of what's going on, especially on the interaction ones. All right, so now how do we determine degrees of freedom? I mentioned this briefly already when we looked at the table, but for main effects, it's going to be number of levels minus 1. Interaction, it's the product of the degrees of freedom that we just talked about. And notice that I've got a product here also. My error, degrees of freedom, is going to be number of observations minus the product of levels for all of the variables. And then our total degrees of freedom is n minus 1. Now, mean square is always going to be the sum of squared divided by degrees of freedom. And our F statistic is always going to be our mean square divided by our sum of squares error. And then the p-value will be using the F distribution, the F statistic, and the corresponding degrees of freedom. So let's take another look at the sources of variation in Factorial ANOVA. So in Factorial ANOVA, the total variation in the dependent variable can be partitioned into several components, each associated with a different source. Each source of variation represents a way that the dependent variable might change or vary. The sources of variations in a Factorial ANOVA include the main effects, the interaction effects, the error or residual variation, and then the total variation. The main effects, each independent variable has an associated main effect, which is the effect that the factor alone on the dependent variable, averaging over the levels of the other factors. For example, in a two-way ANOVA with factors A and B, there's a main effects, one for factor A and one for factor B. An interaction effect represents a combined effect of two or more factors that is not simply the sum of the main effects. In other words, it indicates that the effect of one factor depends on the level of another factor. For a two-way ANOVA, there is an interaction effect of A and B. In a three-way ANOVA, there are three two-way interactions and one three-way interaction. Now, the error or residual variation represents the variability in the dependent variable that cannot be explained by the main effects and the interaction effects. So this is what cannot be explained by our data and our model. It's considered as random or unexplained variation. And then the total variation is the sum of the variation from each of the sources described above. It represents the overall variability in the dependent variable. So each of these sources of variation is quantified by the sum of squares value, which is a measure of the total amount of variation associated with that source. These are computed in the process of conducting the ANOVA and are displayed in the ANOVA table. Each sum of squares has associated degrees of freedom, and the mean square for each source is computed by dividing the sum of squares by its degrees of freedom. The F statistic for the main and interaction effects are then computed by comparing their mean squares to the mean square of the error. All right, so now let's take a look at calculating the p-values in Factorial ANOVA. So in Factorial ANOVA, p-values are calculated for the main effects and interaction effects using the F statistic associated with that row of the ANOVA table. Each F statistic is a ratio of the mean squares for the effect in question, and the mean squares for the error. So the mean squares of the effect or main effect or interaction and the mean squares of the error gives me that ratio. The F statistic follows an F distribution, which is a family of probability distributions that is determined by 2 degrees of freedom. The degrees of freedom for the numerator and the degrees of freedom for the error or the denominator. Once the F statistic is calculated, it is compared to this F distribution to determine the p-value. The p-value is the probability of obtaining that F statistic or one that is more extreme than the observed F statistic value under the null hypothesis that the effect in question has no impact on the dependent variable. Mathematically, the F statistic for a given factor or interaction is calculated as mean squared divided by mean square error. And the p-value is the probability of observing that extreme of an F statistic or more given the degrees of freedom that we have in our data. And that gives us the p-value. And this p comes from the cumulative distribution function for the F distribution. If the p-value is small, typically 0.05, this suggests that it is unlikely we will observe the data that we have under the null hypothesis if the null hypothesis is correct, leading us to reject the null hypothesis in favor of the alternative. All right, so now let's run through an example using R. Okay, so once again, we're going to do 3-way ANOVA just to make our lives a little bit easier than what we could be doing. And we're going to generate some data, 3 factors, A, B, and C, and a response variable. Each factor will have 2 levels, and we'll assume there are 10 observations for each combination of factor levels. So here I'm setting up my random number generator. Here I am saying that I want 10 levels or 10 observations per combination of A, B, and C. Now I'm generating my data. I'm generating my normally distributed. I'm putting everything into a data frame so I can drop it into ANOVA. And I'm making sure that everything is, okay, in this part, this is a little bit tricky, but I'm going to show you something towards the end of my box plots that I need for this. All right, now something I'm doing, I'm setting it up so that we actually have different means for each of our different levels. And I'm saying that we have, so there, in this presentation, the different subgroups are going to have different population averages of multiples of 3. That's what I'm doing here. And we're always going to have a standard deviation of 5. So we have that constant variance reached. We know from generating the data, I know that I have the normality assumption met. And since I generated the data, I know that each subgroup has a different population mean. Now, we want to see, does our test detect this? All right, so let's go ahead and run our 3-way ANOVA. So what I need to do, I need to say that my response depends on, see, I've got tilde, A times B times C. I'm using, the star thing. Okay, so what's happening here? If I have a plus sign, I'm saying main effects. If I'm having a colon, I'm saying interaction effect. If I say star between them, I'm saying include everything from this main effect, for everything in this interaction effects down to main effects. And so when I do this, I'm saying include interaction between A, B, and C, include all of the corresponding pairs of interaction, and include the main effects. So fastest way to get all our formulas spit out. Now, the first one I want to study is my highest order interaction. I look here, and that is not statistically significant. All right, so I know, I conclude, if this was real life, I would conclude that higher order interaction is not appropriate. I'm going to kick it out. So immediately, I'm going to reduce down my model. Now, what I'm going to do is I want to have all of these pairwise interactions considered plus all the main effects. So what we do here, I have the same model, but now I'm going to remove the 3-way interaction. Notice I do a subtraction here. Now, when I do that, I see, hey, I've got interaction BC, interaction AC, interaction AB. Okay, so I have 3 things going on, and it looks like at least one of these interactions don't belong. Okay, so notice that I haven't even looked at main effects yet. I don't consider it. I want you to notice that the numbers here did change when I did this. That's important. You'll notice that they didn't shift a heck of a lot. If I have multicollinearity, by removing a variable, I can have big shifts when there is multicollinearity. We want the simplest model that that accounts for the same amount of variation. So what I want to do, I want to get rid of the 3-way interaction. Now I'm looking at my pairwise interaction. And you know what? And there's a couple ways to go about it. I'm going to go ahead and say, this is the largest p-value. I'm going to remove pairwise AB. And so now I'm manually going through. I have my main effects, and I have pairwise AC, pairwise BC interaction. And so now you'll notice that these numbers are shifting again. You'll notice that, hey, this p-value got a little bit smaller. This p-value got a little bit smaller also. So as I remove things, my test will become more sensitive if there's a multicollinearity aspect going on. All right, so I look here and I say, you know what? I should probably remove AC from there. It's my initials. And so now I remove it, and you'll notice that once again, this p-value has gotten smaller, but I still feel like I need to remove it. So I've concluded at this point that I might want a main effects only model for this data. Okay, so when I do that, I do all main effects, and boom, we have statistical significance every single time. All right, we got some good stuff going on here. Now, all three of these are statistically significant. All right, so I'm done removing things from my model. So let's go through and let's actually visualize what's going on. So I'm going to go through, let's visualize the main effect of A. All right, so what I want to see, ideally, when I look at the box plots to check for different population averages, I want to see the boxes like this. They don't horizontally line up. Here they do. Even though A is statistically significant, they do line up. If I have greater variability, smaller sample size, this may not be statistically significant. What I would like to see for strong statistical difference, or statistically significant, I want to see a big difference. So specifically, I want to see that this median line does not cut this box. This median line does not cut this one. Why I shoot it out horizontally. Now B, these look pretty close to me. Honestly, if I was eyeballing the data before running my hypothesis test, I would have been prone to say that there's no statistical difference off of this box plot. I would have been leaning towards no statistical difference in, just from looking at the box plots. Now here, this is what I like to see to make myself feel confident that there's a statistical difference. We see that this box horizontally does not cut the range of the other box, or and vice versa. So C looks very strong to me. And now here, no, if I was to go through and I can look at all three. So here, this is how one way to look at the three-way interaction is if I put all of these. Now, as I look through these, what I want to see boxes that don't overlap with each other. And individually on the interaction, we can see that we've got like overlapping, like there might be a difference here. This median is cutting the box here. So I'm feeling like the interaction, just observing, I might be able to trim it off just by looking at this one. Now, when I line up my box plots, I took the time to set it up so that the interaction levels were ordered by the mean or median. I can't remember which one I did. One of the two, I think a median. So whenever you do that, like I did, the far left and the far right box plots are almost always going to look very different from each other. And by coloring by C, you can definitely see like the impact. That C looks very strong for this one. Of the three main effects, C looks like it has the biggest impact. All right, so now let's talk about approaching the same problem using linear regression instead of factorial ANOVA. So really, we can approach the same problem in two different ways. We can either use ANOVA or we can use linear regression in dummy variables. Factorial ANOVA and linear regression with all categorical independent variables can both be used to examine the relationship between categorical independent variables and a continuous dependent variable. However, there are some key distinctions between these two methods. The first one is purpose. Factorial ANOVA is primarily used to test a hypothesis and draw conclusions about the population parameters. Specifically, ANOVA is interested in whether the means of the dependent variable are the same across different levels for each factor. It can also assess interaction effects between factors. Linear regression, on the other hand, is primarily used for like predictive purposes. It determines the relationship between the independent variables, predictors, and the dependent variable, which allows for predictions of the dependent variable based on the values of the predictor. When the predictors are all categorical, Linear regression estimates the difference in the means of the dependent variable between different levels of each factor. So this is actually similar to ANOVA. Now, the model representation is different. In Factorial ANOVA, the model is represented in a way that directly shows the main effects of each factor and their interactions. In a linear regression model with categorical predictors, the predictors need to be recoded into a set of binary dummy variables. One level for each factor is taken as a reference, and the coefficients of the dummy variables represents the difference in the means between the reference level and the respective level. So it gets a little bit complicated here. For hypothesis testing, in a Factorial ANOVA, the null hypothesis is that all population means are equal for the factor. An F-test is used to decide whether to reject the null hypothesis. In linear regression, with all categorical predictors, the null hypothesis is that the coefficient of the dummy variables are all 0. The means of the different levels of the factors are all the same. A t-test is used for each coefficient to decide whether to reject this null hypothesis. Now, for assumptions, both methods require the assumptions of independence, homogeneity of variances, and normally distributed residuals. However, linear regression also requires a linearity between the predictors and the outcome, which is automatically fulfilled when all predictors are categorical. Now, for the interpretation, this is where there is probably the biggest difference. ANOVA provides an overall F statistic for each factor and interaction, telling us whether there are any differences in overall means. But it doesn't tell us where those differences are. Post hoc tests are often needed for pairwise comparison. In regression, the coefficients for each level of the factors except the reference level are provided directly, which is nice, showing us where the differences lie. However, to understand the interaction between factors, the interpretation can get pretty complicated. In practice, when all predictors are categorical, a Factorial ANOVA and a linear regression with dummy variables will provide the same results in terms of significance of effect. The choice between them often depends on the main goal of your analysis, whether you're trying to do prediction or hypothesis testing, and the preferences for interpreting results, such as, do you want to interpret regression coefficients or mean differences? All right. Well, that's all I've got for you. Life is short. Do math.